So I'd now like to introduce Claude Alain, who's a professor at the Department of Psychology and Medical Sciences at the University of Toronto, as well as a senior scientist at the Rotman Research Institute at Baycrest Center, and also assistant director, if I understand correctly. Claude.
Thank you. Okay. So I love these computer things. It's kind of a cognitive flexibility in aging. You have to figure things out and okay, let's see where we are. All right. Okay, well, first I'd like to thank the organizing committee for inviting me. This is a great honor and pleasure to be here. And so when I work on this presentation, I was not so sure which way to go anyway. I tried something, we'll see how it goes. The title of my talk is Auditory Scene Analysis from Sound to Meaning, but you know, after thinking about it, it could easily have been how Hal's book influenced my research. But then I thought it was a little bit self-centered, so I decided to go with how Hal's book is shaping auditory neuroscience, and that might be a little bit more appropriate. I think for those that have read the book and have been using information in the book is a wonderful, it's a comprehensive accumulation of information from at least 2 to 3 decades of research on auditory stream segregation, music, and some very interesting idea about object perception and so on. And to me, essentially what is in the book is that Hal, he brought it all together. and the uniqueness is that it provides some sort of a framework that allow people from different fields that were not necessarily talking with each other at the time, and were kind of operating in parallel. And then we were starting to work, and the book is really providing this kind of framework and platform and a common language. And I think this is, to me, where the book has been tremendous. Now, in science, scientists love to try to quantify things. And so when we think about the impact of a book, we always, well, one of the things, and we look at objective measure. One of them is citation index. This is an example using Web of Science citation. And this is not a cumulative citation index. This is the number of times the book is cited per year, starting in 1990 up to 2013. And what you can see essentially is a steady increase in citation of the book. And what it showed or tell me essentially is that the field of auditory research is very vibrant. And I think this vibrancy, this energy that we have in auditory neuroscience these days, and auditory psychology in general, is doing part of these 3 books that we are honoring this 2 days. Now, a lot of things happen. Do we have a pointer? A lot of happened 25 years ago. And what I'd like to do is do a little bit of fun facts. It's a little bit similar to Carolyn, except for whatever reason I decided to hook on 1989 instead of 1990, but I think it's okay. Well, in 99, George W. Bush succeeded Ronald Reagan as the 41st president of the United States. The Exxon Valdez spilled a lot of gas along the Alaskan coast. And this is a hockey town, and I cannot go without that. Ron Extall, which goalie, became the first goaltender in NHL history to score a goal in the playoff. Now, you may start to wonder, where is he going with all this? Well, it's almost there. In 25 years ago, it was the creation of the Rotman Research Institute. About 3 or 4 years after that, it was the creation of the Society for Cognitive Neuroscience. So there was really a conjecture of things that was happening in science at that time. And well, in 1989, I was working on my PhD thesis. Well, and what I'll do now is take a little detour to explain how did I came about auditory scene analysis and how did it influence. And I think my example is probably the same as others that touch into the field, and that might give you an idea of how it impacts. When I was a grad student, essentially I was interested in auditory selective attention, especially the neural correlate. And the way we were studying that at the time was to present a stream of sounds either on the left ear or the right ear, and then to ask participants to detect some sort of a small target in the designated channel. And what we usually do in those days is we adjust the discriminability of the target so that we force people to pay attention to the information channel that we define as either the left or right ear. Now, when you measure auditory evoked potential, that sort of experimental manipulation, you see that the evoked response for the stimuli that occur at the attended location are larger than the one that occur at the non-attended location, even for the same stimulus. So that's fine. That was shown in 1973 by Steve Hilliard. Now, subsequently, people become very interested in trying to characterize what is mitigating and what is influencing this effect of attention. And they start manipulating all sort of variables. One of them was frequency separation. So people start to having a very small separation between the attended and non-attended channel. Then they increase. And the effect of attention is illustrated in the difference wave right here. And what you can see is as we increase the frequency separation, we see a larger attention effect and earlier response. And that kind of manipulation has been seen for the type of features changing, for example, the spatial separation of the task-relevant and task-irrelevant channel and so on. People also shown that if you manipulate the stimulation rate, when you present sounds at a higher rate, it's easier to attend to the attended channel than if you present at a slow rate. And again, you have this larger attention effect compared to the case where it's presented slowly. Now, for those that have done a little bit of research on auditory scene analysis or dip into those issues, it's interesting, the same parameters that are modulating the effect of attention essentially are also there to produce or favor or promote stream segregation. So it came to what are we attending to? And that was the type of question I was struggling at the time in 1989. So one idea at the time is that we were having some sort of a template of the attended channel, which was usually defined by dominant features, example, location or pitch. The problem, however, with that view is that you could also have a case where you were attending to an object, to a stream, as opposed to the pitch in itself. So it was difficult to know what was the unit of selection. Was it the feature? Was it the object? So in the early studies, essentially all the way to 1990, in fact, to when we start, all the auditory attention study at the time were essentially confounding object and pitch. So at the time, I was lucky. I was working and studying in Montreal, and my lab mate was André Hachim, who worked with Al Bregman. And in our many conversations, he started to say, well, Claude, maybe you should meet with Hal and discuss your ideas, because there's something about streaming that you seem to be interested in. So at the time, I called, because there was no email, and tried to set up a meeting with Al, and we met. And so I did the trek, the trek between University of Quebec and Montreal to McGill. And we have this conversation. And you have to understand, I'm coming from human electrophysiology and selective attention. I'm very interested in making sure that I can measure accurately these evoked potential. So I have some constraint. I want to present sounds in a random orders, and I want to present in random interval and so on. So I explained to him what I want to do, cluster things and group sounds together. And he looked at me, he's not so sure. He said, and I said, do you think it's going to stream if I was to do that? He said, I'm not sure. But he felt, I guess, a little bit sorry for me, because he at the time, he provided me with, and I think also he was not so sure, because I didn't know if he understand exactly what I was trying to explain. Now, if you think I have an accent when I speak English now, try to imagine 25 years ago, was I coming fresh from Quebec City. So it was quite of a feast for him to decipher what I was trying to explain. Anyway, he gave me at the time these 2 chapters of his book, which was in press. So I had a sneak preview to the book before it was published. So that was quite interesting. So I went through these chapters and returned them after a few months, and went on to integrate some of the design, some of the ideas that were there. And one of the studies that I'd like to describe very briefly that we did is inspired on one of the studies was published in 1975. And the idea here essentially was to pit against each other pitch features or feature and objectness. And the way we did it essentially was to have a baseline condition where we have 3 streams of sounds that were evenly spaced. And then they have to detect a small target at that attended location. And then what we did is to cluster together the 2 distractor sounds. The idea here is, from a feature base, what you would do, essentially you would have increased the number of distractors that are nearby the attended frequency. So if anything, you would cause more interference, or maybe nothing at all, because the distance is far enough. But from an object perspective or streaming perspective, you should promote the clustering, the grouping, and that should be easier for the subject to ignore that stream of sounds, and therefore they should be doing better. And we have a control condition where we cluster together the attended channel with the middle frequency, which in this case, because the sound is closer in pitch, should cause more distraction. There's always a good ending to those stories. That's what we found. This is the reaction time for that sort of a manipulation, which is intermediate. And when we cluster together the distractor, then they get quicker and more accurate. And when we mix them with the higher, with the middle frequency, then they get slower and make more mistakes. When we measure evoked potential, bingo, we got this larger attention effect when we were clustering in situations that did promote the segregation, the separation of those distractors from the task-relevant channel, and then the opposite when we mix the two. So that was essentially finding that was one of the study. We did many others, but what this shift in combining design of selective attention with streaming paradigm or manipulation kind of changed a little bit the way we're thinking about attention at that time and in the future. And that led to the foundation to the subject-based account of auditory attention that we essentially proposed in 2000, but also Sean Cunningham proposed in 2008 as well. Now, the effect of distractor clustering in that study was taking as evidence that sounds are automatically grouped together, even when they were presented outside the focus of attention. But that was an attention study, so how can you know that it was independent of attention? So one could ask the question, would you get perceptual organization when people are really doing something else, for example, doing a visual task? And one way to do that is to use a paradigm that we call a mismatch negativity or the oddball paradigm. And this is a paradigm that's been quite popular at the beginning, again, in the 70s and 80s, to look at sensory memory. How do we represent acoustical features? But subsequently it's been used to look at more abstract representation, perceptual pattern and music perception and so on. So the typical paradigm is very simple. You have a stream of sound, you get a beep and boop, and then you have, this is a schematic representation of waveform you can record in those situations. This is the mismatch wave. This is a real wave that you record in that sort of paradigm. And the difference wave is typically used to isolate the mismatch response. And this is you can use to look at representation of pitch, location, intensity, duration. People have used subsequently in the 80s, for example, tone that alternate and pitch, four-tone pattern. People play with musical sequence, looking at change in temporal interval and so on, and pitch interval. And with that, one of the first study, in my knowledge, I think that used that approach to try to learn a little bit more about streaming was a study by Elise Sussman, who used the original paradigm from Bregman in 1971. So if you play those 6 sounds in a slow rate in alternation, essentially you can integrate them in one stream. But if you increase the rate fast enough, then the sequence split together into 2 perceptual streams. So Elise did a little trick to it. She essentially added deviant sound in the high stream sounds and the low stream sounds as well. And her idea was that at the time, well, if the sequence is organized, then they should not notice much of that change in pitch because the alternation keep on going. But that change when the sequence is streaming should pop out quite dramatically. And this is essentially what she found with respect to mismatch negativity. There was no significant responses at the slow rate, but she did notice but she did notice this mismatch response when things were presented at a high rate, therefore promoting stream segregation. So that was taken at the time as evidence that stream segregation can occur or is independent of attention. And that was consistent with some behavioral study at the time was looking at infants, for example, where you wouldn't think that they can voluntarily attend to one stream or another. And it was also consistent with some animal work done with anesthetized animals, for example, showing some changes in neural activity that appeared to index frequency separation or stimulation rate like that. However, there's a little bit of a caveat. Around the same time in the 90s, in the early 90s, a group from England, Bob Callion and his colleague, showed that if you manipulate attention, that would affect essentially the buildup of auditory stream segregation. And that generated a number of other research looking, or a mini debate, if you wish, between to what extent streaming might be automatic versus to what extent it may need attention. I don't want to go too far on that path, and I would like to take a different direction very quickly. And it's just to discuss a little bit of studies that look at that go beyond this attention debate, essentially looking at perception in itself. How do we perceive, and whether there's some neural correlate of this perception. And one of the things that the book has provided to a lot of neuroscientists is a numbers of beautiful paradigm to look at bistable perception. And this is a situation where you have identical stimulus but a different percept, or that will generate different percept. One of the paradigms that was very popular was the ABA paradigm. And that was introduced by Van Noorden, essentially. So if you play this triplet of sounds at a low rate, you hear a gallop rhythm, but if you play at a high rate, then it's split into two streams, and I'm not going to sing that pattern. It's pretty hard. What is nice about the paradigm, and that was described by Van Noorden at the time, is that you have area where things are always streaming when you manipulate the frequency separation and the rate of presentation. And you also have an area that is always consistent, but you have a huge area where things are ambiguous, where people start to hear one stream or two stream, and their perception alternate back and forth. And Sue Denham and Itz van Winkler, they've done quite a bit of work looking at using behavioral technique, using very long sentences and try to understand how do we go back and forth and so on. There's also some work from Jules Snyder, a former postdoc of mine, who's also looking at the impact of context on stream segregation, and again, try to keep constant the stimulus and looking more at different percept. Now, one study I'd like to mention quickly is a study done by Gunstock, who used this ABA paradigm. It was the first study, to my knowledge, who combined, again, the streaming paradigm with neuroimaging. In this case, it was using, not neuroimaging, I should say, but with MEG. And essentially what he found is that as you increase the frequency separation, not surprisingly, you would find some change in neural activity that's coming from the auditory cortex. And what he did, not surprisingly, found a very nice relationship between the increase in frequency separation and the perception of two stream, and that percept correlate with change in neural activity there. Subsequent work using fMRI also shows some very nice changes that occur on the axial gyrus as well as the planum temporale, and that follow nicely the increase in frequency separation between the sound. And that increase in neural activation essentially was taking as evidence or as a demonstration of an idea that may be, or a neural mechanism that may underlying stream segregation, which is the population theory of streaming. Essentially, the idea that you would have, when you get streaming, it's because you're getting activation in two different neuronal populations. You have an extension of the area that is getting activated. Now, what I'd like to do, however, is to go back to the study from Gunstock. And what he did in his study is to take the intermediate case where it was ambiguous, and essentially he re-averaged his evoked response according to the percept. And what he found is a very nice modulation in neural activity coming from the auditory cortex, indicating that the change in neural activity that we see in the superior temporal gyrus is not only reflecting a change in the acoustic feature leading to stream segregation, but it seems to be related to some extent to the actual perception of these events, independently of a difference in acoustic dimension. There's been some subsequent study now using fMRI that I've seen the other area that might be involved in the perception. So from here, what I'd like to do in the last 5 minutes that I have is to bring you to a different direction a little bit. This is a new direction we're taking from my group, where instead of looking at different, or taking snapshot of the system, looking at the auditory cortex, for example, we try to look at change in neural activity that happen all the way through the system. And the way we do that, this is a very popular young lady, has been in a lot of experiments. And so we have that young person, we present various sounds, and we present it at various rate and different condition. Rate enough that we can record a lot of trial, and we can use a sampling rate allow us to look even at brainstem activity so that it's rigged on the top of this kind of slow activity that you have there. And what we do essentially, we apply two different filters. A filter that allows us to extract our cortical evoked response, and at the same time, we can extract brainstem event-related potential, the frequency following response. And now the question that we're asking essentially is, what is the relation between the activity that happened in brainstem with that of the cortex, and how the activity in the cortex will predict the behavior? So we're starting to look to use more what we call a system approach as opposed to a snapshot approach. Now, I'm not going to go in detail on this thing. I'm going to flip through the slide very fast, and you'll have to take my word granted for it. This is an example I'm going to give you is for concurrent sound segregation. In this case, we were manipulating we use the Mistune harmonic paradigm. So essentially, if you have pure tones stacked together, they fuse into one object. If you mistune the lower harmonic, you hear two sounds, a buzz plus another sound with a pure tone quality. Now, you can use this approach, essentially, you can ask the question, oh, what are people perceiving? Then you can look at cortical activity, how does it relate to change in brain activity? Then you can look at the brainstem. And in that particular example I'm going to give you, we even used a computational model from the auditory nerve and fed our stimuli to see what kind of output we would get. And this is just looking at the behavioral performance. Not surprisingly, as you increase the amount of mistuning, the likelihood of hearing two things increase. And the reaction time also increase, especially when you have an ambiguous case where things are not clear. Now, this is the evoked potential. Those are the cortical evoked response for the two extreme cases. And we can compute a difference wave. The first wave that we call here is what we call the object-relate negativity. It seems to be related to the segregation of these events based on frequency periodicity. But we also have other components, like a P400 at this N5 component, the lake wave. Now, the ORN seems to be really closely related to the amount of mistuning. But this 500 component, or this component about 500 milliseconds, is related to the percept of the subject. So if you know exactly what it is, whether there's one object or two objects, you get a larger response. If you don't know at all, it's very ambiguous, you get the smallest response, and then something in between when you're not so sure. Now, what about the brainstem? Well, this is a brainstem evoked response. We can calculate a fast Fourier transform. From there, we can have a neural harmonicity index, and then we can see how that index covariates as a function of the amount of mistuning. And here we have roughly some sort of a linear function that go there. And then we can go with the auditory nerve response, and then we can feed our stimuli through that, take the output of that model and see how to apply the same pitch sieve and see how does it map. And then this is for the behavior, and we have something that interestingly seems to match on a little bit closer to the behavior there. And then what you can do obviously is various correlation that you can compute there between the auditory nerve and the ERP, the auditory nerve and the behavior, and the ERP and the behavior, and try to get a best mapping. So essentially this is just to illustrate the approach that we are now taking from my group, looking at multiple steps simultaneously. So what I'd like to argue, and what I'd like to see in the near future, is we'd like to see that we believe that examining multiple tiers of brain activity simultaneously is probably the best way to capture representation and emergent percept as opposed to taking single snapshot. We've been using a similar approach to look at categorical speech perception as well as the effect of musical expertise and the impact of aging on speech representation. So the next challenge for us essentially would be to try to understand how the response is changing from the brainstem for the cortex. What are the algorithms that translate the signal and so on? So this is going to be the next challenge. So if I try to kind of wrap it up together, from my perspective, the book has been tremendous. It has been a magnet, essentially, to bring together different people with different background and different expertise, and then to tackle different questions, and then take some bit and pieces, perhaps, from that scene analysis framework to bring in their own research, whether it's on speech perception and noise, music perception, and so on. And it's been instrumental in developing research in auditory neuroscience as well as computational neuroscience. And I think what we're going to see perhaps in the future is an increased interaction between auditory neuroscience and computational neuroscience, and try to understand these interaction that was just described. So thank you very much for your attention.